This lesson is, in my opinion, when things actually start getting more interesting and when the use of differentiation actually shows all its power. We are studying now the monotony of functions. What is this? This is a study on how functions change, if they are increasing or decreasing. Okay? So let's take again the example of the function x squared and its tangent gradients. Okay, so here you have x squared. I picked these 5 points, and then I just substituted these x coordinates on the expression for the derivatives, and I have here the tangents of the function x squared on these points. So basically, I have here the x squared, and here the tangents on these, the gradients of the tangents, that is, on these 5 points. So -4, -2, 0, 2, and 4. What does this mean? If you compare the gradients on of this point, on this point, and on this point, so I'm talking about the gradient 2 and 4 on points with x coordinate 1 and 2. This means what? This means that the function is increasing more rapidly on this point, the 2, 4, than on point 1, 1, right? I already talked about this in the previous lesson. The gradient, the value of the gradient, is a good measurement of how the function is evolving, how the y is evolving in relation to x, whatever y and x may be. All right, so the value 4 is bigger than 2, so y is changing more rapidly in relation to x over here than over here, right? Let that sink in because this is very important. Let's now compare the gradients on point -1 and 1, so over here and over there. On point -1, 1, the gradient is -2, and on point 1, 1, the gradient is 2. So what does this mean now? This means that here the function is decreasing, and here it is increasing. Look, as you are going over here, what is happening to the function? It is going down, right? So it is decreasing. Over here, it is increasing, okay? So the gradient itself, the sign of the gradient, will give you information about how the monotony of the function is, if it is decreasing or increasing. If the gradient is negative, like over here, the function is decreasing. If the gradient is positive, the function is increasing, right? What if the gradient is 0? If the gradient is 0, you have a very, very, very high probability that this is a point where a function stops decreasing and starts increasing, or vice versa. In this case, the point 0, 0 is the point where, well, the function is neither increasing or decreasing. It's actually changing from decreasing to increasing if you go that way. Okay? Let's now look at the more general function, which I just represented by this random blue line. And let's just look at it and identify different parts of it. So on this part over here, it is increasing, right? It's increasing, increasing, increasing. Here you have a maximum. From this point onwards, it starts decreasing. It's decreasing, decreasing, decreasing. But here, it starts increasing again. So here you have a minimum. It starts increasing, increasing, but then not as fast. And here it seems that it's going to start decreasing, but no, actually resumes its increasing thing. Okay? So increasing, decreasing, increasing, and here continues increasing. All right? If you look at these points over here, which I named with the x coordinates A, B, and C, what can you see? You see that here you have these lines over here, which we are going to see in a bit. These are going to be the gradients of the function on these points. And these are going to be very important for you to identify the sections of the function in which the function is increasing or decreasing. But before that, let's look at any value of x that is smaller than a. We already saw that the function is increasing. Now, let's imagine that you wouldn't have access to the sketch of the function. How could you figure this out? You know that the derivative of the original function for any value of x that is smaller than a is going to be positive. F dash of x is going to be positive until x, for any value of x that is smaller than a, right? You already know what this means. This is the gradient of the function on any point. For any point that is smaller than a, the gradient is positive, as you can see here by the pen. It goes straight up, it's positive, it's getting less positive, but still positive, until this point a. What is happening between a and b? Look at the pen. It's negative, right? The inclination goes down. In all these values, the gradient is negative. So f dash of x is smaller than 0 for any value of x between a and b. F of x is decreasing. Okay? Before it was increasing, here is decreasing. What is happening from b until c? Actually, from b onwards. From b onwards, the gradient is positive, with the exception of this point over here. The gradient is positive, so the function is increasing. All right? Actually, I included here as bigger or equal to 0, just because of this point where it is 0. What is happening on point A? The gradient is 0. What is happening on point B? The gradient is 0. What is the importance of the points where the gradients are 0? They are very good indicators that this is going to divide a function into a section where it is increasing to a section where it is decreasing, and vice versa. This first point A divides the function in a section where it is increasing to a section where it is decreasing. Then this point B divides the function from a section that is decreasing, that I mentioned before, to another one where it is increasing. Okay? It doesn't necessarily mean that every single point that you find with gradient 0 is going to do such thing. Look at this one over here. This is not very common, though, okay? And chances are, and 90% of the times you will find these points, they are actually going to divide functions from increasing to decreasing or vice versa. But you may find these points over here where the gradient is 0, but they actually don't change the monotony, okay? So, on point x equals a, this is called a maximum, as you can see here for a long time. This is called a maximum, the maximum point of the function, at least in this section. This is going to be a minimum point. And this is going to be called a point of inflection. But all of them, globally, they are called stationary points. From now on, you are going to hear a lot about this in questions, and every time you read this, you need to know automatically that these are points where the gradient of the function is 0. And chances are, in 90% of the case, as I mentioned, that they are either going to be a maximum or a minimum. If they are a maximum, the function is increasing and then starts decreasing. If they are a minimum, the function is decreasing and then starts increasing. Okay? There is, however, a more... Actually, before talking about this, let's say that you want to figure out the coordinate of a stationary point. You are given the expression for the function, whatever it is, and the question is just, find the coordinates of any stationary point. What do you have to do? Just by looking at this. If you think a little bit, what you have to do, you have to get the expression for the gradients and equal it to 0. The stationary points are the points where the gradients are 0, right? So if you want to calculate the coordinates of the stationary point, first of all, you have to differentiate the original function. so that you have the function of all possible of all possible gradients, and then equal this function to 0 and solve it. You're going to have an equation. You solve it by equaling it to 0, and then the values of x that you are going to have as the solution of that function are going to be the x coordinates of the stationary points. If you want to get the y coordinates, substitute these values on the original function and you get the y coordinates. Making sense? This is a very typical question. And as typical as this question is the question that comes after that, which is, are these stationary points that you just found a maxima or minima? Are they a maximum or a minimum, each one of them, or a point of inflection? Then I'm just going to give you the straightforward way to solve it. But even without the straightforward way, you could just test it. Let's imagine that the function was this one, and you just found this x coordinate a, whatever it is. But since you don't have access to the picture, you don't know if it is a maximum or a minimum. What could you do? If you would use a value that is very close to a, but to the left, okay? So a minus a bit, all right? A minus 1, whatever a is. So let's say, for the sake of argument, let's say that a is minus 5 in this particular question. If you would test not for minus 5, but for minus 6, and if you would plug minus 6 on the expression of the gradients, what would you have? You would have a slightly but positive gradient, right? If you would test now for minus 5 plus 1, so let's say minus 4, what would you have? You would have a negative gradient. Again, what are we doing? We are playing two different values that are close to a, to the left and to the right, where? On the expression of the gradients. So if it is a maximum, the gradient of the line that of the point that is to the left of a is going to be positive, and to the right of a is going to be negative. And this proves that the value of a is a maximum. Similarly, if you would do the same thing but here for value b, so the gradient of the line that would be to the left of point B would be negative, and to the right of point B would be positive, and this alone would indicate that B is a minimum. What about that one? If you do the same thing over here, this value will be positive, and this value will be positive as well. If you will have something like this, then one would be negative and the other one would be negative as well. When the inclination of the gradient of points that are to the left and to the right of a stationary point have the same sign, either positive, as in this case, or negative, then those points are points of inflection. All right? This is a method to figure out the nature of the stationary point. This is another way they use to ask the same thing. Find the nature of the stationary point. Basically, you are being asked if the stationary point is a maxima, a minima, or a point of inflection. What I just told you was one way of doing that. But there is a more straightforward way, which I'm going to explain first, which I'm going to tell first and explain after. What is the method? The method is this. At this point, don't forget, you already know the coordinates of the stationary points. You are just being asked about its nature. So what do? You differentiate the function of the gradients again. So you find the second derivative. All right? Second derivative means what? Means what it suggests. It's the derivative of the derivative. Okay? So before you have differentiated the function to get the expression of the gradients, differentiate now this one again, and you are going to have the second derivative. It's also going to be a mathematical expression, okay? So determine the second derivative of the function. It's represented by y double dash or f double dash of x, or d square of y by dx square. All of these mean the same. These are the second derivatives, and they are going to be mathematical expressions, okay? What do you do with that then? You just substitute on whatever you get out of that, You substitute x by the x coordinate of the stationary point that you are studying. All right? You already know from the previous question the coordinates of the stationary point. Pick up the x coordinate, plug it over here, and you are going to have a number. And then all you have to do is look not the value of the number, but just the sign. If that number is positive, then the stationary point is going to be a minimum. If that number is negative, then the stationary point is going to be a maximum. If the gradient, if the value is 0, then the stationary point is just a point of inflection. All right? I'm going to say again, it's very simple. You already know the expression of all gradients. From that, you already calculated the coordinates of the stationary points. We are now trying to figure out what is the nature of these stationary points. So the method is differentiate the expression of the gradients again. You will have a mathematical expression. Substitute on that mathematical expression x by the x coordinate of the stationary point that you are studying, and you are going to get a number. If that number is positive, then the stationary point is a minimum. If it is negative, the stationary point is a maximum. Look here, this is counterintuitive, okay? Positive is minimum, negative is maximum. If it is 0, it's just a point of inflection, all right? To illustrate this, I'm going to use again, I'm going to use this function over here. So I use this x cubed minus 3x squared. It is represented here by this blue line. I just differentiated to get the expression of all gradients. That's 3x squared minus xx. And I already found the second derivative. So I differentiate this again, and this is the mathematical expression that you will get. I'm going to take this opportunity for you to look at the different graphs that you have here. So don't forget, in blue is the function that you are actually studying. Then I represented in orange over here. This is going to be this parabola over here. Another function, which is the function that will give you all possible gradients. Okay? Just substitute x by whatever value, and you have the gradient of the blue one given here by this parabola. And then I also bothered to draw this straight line over here would be the representation of the second derivative. Okay? I just picked these random 6 points ranging from -1 to 4. I have here the y coordinates of all of them. Okay, I plotted them here with the blue crosses. And let's see what's happening to the gradients. So the gradient is positive and big. It's still positive, getting smaller and smaller. Here the gradient is 0. Here is negative and getting more negative until this point. This is as negative as it gets. Now it's still negative, but starts getting less negative, right? Over here is 0, and now gets positive again. This what I just described is represented here in orange. Again, I'm going to do it again, and look at the orange. Big and positive, but getting less positive, but still positive. Here it's 0. Now it starts getting negative. Here is the maximum negative value that it gets. Now it's still negative, but getting less negative. Over here is 0, and starts then getting more and more positive. Did you just see how this represents what is happening to the gradient of the original function? You can take a similar approach to the second function, all right, which is the pink one over here. If you do the gradient of the gradients, of the expression of the gradients, it starts as being negative. It's still negative, but getting less negative. Over here, it's where the gradient is going to be 0. And now it starts getting positive and more positive. All right? All of that to say what? And now how does this relate with what we were talking about? If you look at the original function, the stationary points, you can spot them automatically by looking at the function. It's going to be this point over here and that point over there, right? And by looking at this, you know that this is a maximum and this is a minimum. But the question is always, if you don't have access to that, how would you know? Well, if you get the expression of all possible gradients, that is, if you differentiate the original function and equal it to 0, by solving this, you would get them as a solution to that function, the values 0 and 2. Okay? If you want, just try it out. Factorize x, then you'll have 3x minus 6 equals 0. So you have x equals 0 and x equals 2. These are the x coordinates of the stationary points. But you don't know yet if they are maximum or minimum. So what do you have to do according to the instructions I just gave you? Differentiate this again, and you'll have that. And now substitute x by 0 and x by, 2, and see what you get. If you substitute here x by 0, you have the value minus 6. If you substitute x by 2, you have the value 6. This is a negative number. That's all you have to look at. It's a negative number, so it means it is a maximum. It's this one over here. This one is a positive number, so it means it is a minimum. This one over here.